Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast covers electrochemistry. I'm going to first start by giving a little bit of an introduction to electrochemistry, talk about some basic definitions, talk about the three different types of electrochemical cells to know. Then I'll get into thermodynamics. I'll talk a little bit about Gibbs free energy. I'll talk about the Nernst Equation. And then lastly, I'll talk about a few applications of electrochemistry. The first being electroplating. I'll talk a bit about batteries. And then I'll talk briefly about some of the applications to the human body. And this material is going to show up in one of the four sections. That's going to be the Chem Phys section. And it is pretty important material. I think this is fairly high yield. So with that said, I hope this helps you in your studies, and good luck as you prepare for the MCAT. So in general, electrochemistry is the study of reactions that cause electrons to move. We have talked pretty extensively about one of these types of reactions, and that's going to be a redox reaction, a reduction-oxidation reaction. In terms of the MCAT, you're most likely to see electrochemistry in the context of an electrochemical cell. And so the first thing I want to do here is kind of introduce you to a few of the different types of electrochemical cells, three in particular that you're most likely to see. And I'm going to be talking about these electrochemical cells throughout this podcast. So as I talk about these, just understand that I'm going to definitely talk more about them as I continue to go on. So the first type of cell is called a galvanic or Voltaic cell. And this was named after Luigi Galvani, who is actually the brother of Mario Galvani, probably more well known, and also Alessandro Volta. The second type of cell is called an electrolytic cell. And then the third type of cell, which is actually a type of galvanic cell, is called a concentration cell. So let's start with the first there. So the galvanic cell or voltaic cell is an electrochemical cell that runs spontaneously. And then electrolytic cells are non-spontaneous electrochemical cells. So they need an external source of voltage, like a battery, in order to run. And then, as I said, concentration cell is a type of galvanic cell. But the difference between a galvanic cell and a concentration cell is that in a concentration cell, I have electrodes that are the same metal on both the cathode and the anode. So the cathode and the anode are the same metal, and these metals sit inside solutions of differing concentrations. So what actually powers this cell is the fact that there are different concentrations in the cathode and anode compartment. And that might sound like a lot right now, and you might be like, what does that even mean? And I'm going to get into this more as I introduce these different topics regarding electrochemistry. But just understand for now, concentration cell is a type of cell that has different concentrations of ions in the cathode and anode compartments. And these cathode and anode are usually the same material, the same metal. And one thing to know about all these cells is that in terms of their direction of electron flow, electrons flow from the anode to the cathode. And that's true for the galvanic cells, the electrolytic cells, and the concentration cells. So just keep that in mind. That's a good thing to know. All right, so those are the three types of electrochemical cells to know. And again, I'm going to go over these throughout the podcast. So I just want you to understand what each of those are right now, and you'll get a better understanding as we go. So the next thing I want to talk about here is the structure of an electrochemical cell. There are many ways that you can create an electrochemical cell. The most common representation that I've seen, and probably that you've seen, is the following setup. You have two separate beakers, each containing an electrode and then a solution of metal ions that corresponds to that specific electrode. So for instance, say that I have a copper cathode. Well, the cathode itself is going to be solid copper metal, and then it's going to sit in a solution of copper 2+ ions. And, that can be from the addition of copper sulfate, for instance, you dissolve that into the beaker. So that's the cathode compartment. So now say we have a zinc anode, well then you're going to have zinc metal as the anode, and then it's going to be sitting in a solution of zinc 2+. Again, that could be just dissolved zinc sulfate. And typically the concentration of ions in each of these compartments or beakers is going to be 1 molar. That's just the standard conditions. However, for a concentration cell, that would be something like the anode compartment having a concentration of 1 molar, and then the cathode compartment having a concentration of 0.1 molar. And then both of the cathode and anode would be copper metal. In other words, they'd be the same metal. Okay, now back to this representation of an electrochemical cell. So again, I have 2 different beakers. They each have metal in them, cathode and an anode, and they're in a solution of their own metal ions. Now, the next thing that I typically have is a wire that connects the metal cathode to the anode. And again, electrons flow in the direction from the anode to the cathode. And this wire allows these electrons to do just that. The next component that I'll typically have is a salt bridge. So this is pretty much exactly what it sounds like. It's a bridge between the 2 beakers that contains different salts. And I'll get into the importance of this in a second, but essentially it lets charge move between beakers so that it doesn't accumulate as electrons flow from the anode to the cathode. In other words, the salt bridge functions to maintain a constant net charge in each beaker or each compartment. Electrolytic cells require an external voltage source, so sometimes you'll see a battery or the symbol for a voltage source, which is like 1 line and then a smaller line. You'll see that in the wire that connects the cathode and the anode. On the other hand, a galvanic cell spontaneously produces a current. So sometimes you'll see like a light bulb or a medical device or something that is plugged into this wire that connects the cathode and the anode. So that's kind of the classic picture of an electrochemical cell, right? You got 2 beakers. Each of these beakers contains metal. In one beaker, you have the metal anode. In the other beaker, you have the metal cathode. Each of these electrodes are sitting in a solution of their own ions. And then you have a wire connecting the cathode and the anode. Sometimes you need an external voltage source to make this cell work. That is an electrolytic cell. Sometimes this is spontaneous, in which case you don't need a voltage source. That is a galvanic cell. And then you have a salt bridge that connects these 2 beakers together. And if you Google an image of an electrochemical cell, this is what's probably going to show up. And the last thing I'll say here is that for an electrolytic cell, these electrodes, the cathode and the anode, do not need to be in separate beakers. So you can see representations where basically you have these electrodes in the same beaker, or they're essentially swimming in the same pool. So just keep that in mind. All right, so the next thing I want to do is I want to take these components that I've talked about and break them down and talk more conceptually about what's going on. You know, what's going on at the cathode, what's going on at the anode, what exactly is the salt bridge doing? And I think this stuff is important, right? Because the MCAT doesn't give a shit if you know what an electrochemical cell looks like, right? And you know how to define the different parts. It's going to test you more conceptually and want you to apply some of these concepts to problems. So with that said, let's talk first about what's going on at the cathode and anode. So I've been using the term electrode a lot. An electrode is just the solid metal part of the electrochemical cell. It defines both the cathode and the anode. The cathode is the electrode where reduction occurs. And remember, reduction is gain of electrons. And the cathode is also considered the positive terminal of the electrochemical cell. The anode, on the other hand, is the electrode where oxidation occurs. And if you remember, oxidation is loss of electrons, and the anode is considered the negative terminal of the electrochemical cell. And for me, the cathode being positive and the anode being negative is kind of easy to remember because I remember that electrons flow from the anode to the cathode. So the cathode must be positively charged, right? Because those electrons are flowing from the negative to the positive, right? They're attracted to the positive, they're repelled by the negative. That's just kind of how I remember it. And the mnemonic that really helped me remember what was going on at the cathode and the anode is red cat grr, which is kind of a silly phrase, but it is reduction occurs at the cathode, which is a gain of electrons. So that's how I used. And honestly, when these electrochemistry problems would come up, I'd actually write that down. I'd write down red cat grr and just like put an arrow from cathode, reduction, gain of electrons. So that way I kind of had it all together in my mind, because it's like a 5-layer cake, right? You're cutting through cathode to get to reduction, cutting through reduction to get to gain of electrons. There's like a bunch of different layers to it. So if you can draw that out real fast on your little white erase sheet of paper that you have when you're taking the MCAT, I do that. I like to visually see it. And lastly, you can remember that cats are positive. That's just what I remember. I like cats, so I would say they're positive. That helps me remember which terminal is the positive terminal. It's the cat terminal, the cathode. So now let's talk about this in terms of a real electrochemical cell, one that has zinc at the anode and copper at the cathode. So at the anode, zinc is being oxidized, or it's losing electrons. So essentially what's happening is that the zinc solid is being converted to zinc 2+ ions and 2 electrons. And of course, these electrons are then going up through the wire to the cathode, but meanwhile, you are making more of these zinc 2+ ions, right? Because the anode is actually sitting in a solution of zinc 2+ ions. So over time, as you get more and more of this zinc metal that's oxidized, you're going to start increasing this concentration of zinc 2+ in the anode compartment in that solution, or in that beaker that's containing the solution of zinc. Now, as I said, the electrons that are being released from the zinc metal are traveling up through the wire to then the cathode. And at the cathode, copper is being reduced. So it's gaining electrons. And so what's happening there is that copper 2+ in the solution that is surrounding this cathode is actually reacting with these 2 electrons to then produce solid copper. So over time, you're actually increasing the amount of copper solid that is on that cathode while decreasing the amount of copper 2+ that is in solution. So what I like to think of when I think of a galvanic cell or a galvanic electrochemical cell, I like to think a little bit about a monarchy. So think back to what you know about reduction and reduction potentials. So some compounds have a higher reduction potential than others, meaning that they can take electrons from others or are better at taking electrons in than other compounds. So compounds with higher reduction potentials essentially rip electrons away from compounds with lower electron potentials. So what I like to imagine is that there's a fat red cat that is sitting on the cathode, and he is also a king. And so as all kings are, he's plump and he's greedy, and he likes to take gold from the peasants. And so I imagine then that electrons are like gold, and so these peasants are at the anode, and there's a bunch of peasants. And of course, this fat red cat is just taking gold from these peasants, right? He keeps raising the taxes and just taking more and more of this gold. And so over time, because this fat red cat that's a king, is getting more gold, he can continue to buy more food. And so he just gets fatter and fatter. However, the anode, which is the peasants, they're getting all their money taken from them. So because of that, they can't afford food, and they're getting skinnier and skinnier. And so that kind of is what's happening to the anode and the cathode during this reaction. So then to add to the mnemonic that I already talked about earlier, it could be red, cat, grr, king. It kind of wraps everything up, right? Because that way okay, this is the king, he's taking all the electrons, and he's getting fatter over time as the electrons flow from the anode to the cathode. However, if you were to throw a battery in this electrochemical cell, what would happen? Well, you would reverse the direction of electron flow, and therefore you would reverse which electrode was the cathode and which electrode was the anode. So now, in my fat cat red king analogy, which sounds kind of ridiculous, what's going on is that there's an uprising, and now the peasants actually are pushing democracy, and they kind of switch the direction that this money's flowing. Now all of a sudden they're like, okay, King, we're putting you on trial and we're redistributing all your money. So maybe we're talking more communism here. But anyways, there's an uprising. Now the king's got to give back all its money and the direction changes. And now, the king isn't even a cat anymore, right? It's the anode. And now the peasants are able to all get more food and they start getting more full and the electrons start flowing the other way because the peasants are now the cathode. All right, so all this is to say that electrons flow from the anode to the cathode, and there's reduction that's going on at the cathode, oxidation is going on at the anode. The cathode is growing in size over time as more solid metal accumulates on it as a result of the reduction that's going on at the cathode. And then if you throw a battery into a galvanic cell, all you're doing is reversing the direction of electron flow. Shout out Cha-Cha Slide.
Reverse! Reverse! Slide to the left.
All right, the next thing I want to talk about here are salt bridges and get more into what exactly a salt bridge does for an electrochemical cell. So as I said earlier, the salt bridge connects the cathode solution to the anode solution. So in the two beaker setup that I presented, this is essentially just a bridge between these two beakers. And what this does is it allows for charge in each beaker to remain constant. And I think the easiest way to see what it does is to see what would happen to an electrochemical cell if you didn't have a salt bridge. So if an electrochemical cell did not have a salt bridge, what would happen is that as electrons flowed from the anode to the cathode, there would be a charge imbalance that develops, right? As you have these negative electrons moving to the cathode, over time the cathode would become negative and the anode would become positive. And very quickly, this charge imbalance is going to counter essentially the redox reaction that's occurring that's causing these electrons to flow, and thus the electrochemical cell would be non-functional within a very short period of time. And so what a salt bridge does then is it allows ions in the salt bridge to counteract this uneven charge that develops over time from the flow of electrons. So what happens is you have positively charged ions from the salt bridge migrate into the cathode half cell or the cathode beaker, while negatively charged ions migrate into the anode compartment where electrons are leaving, and thus it's becoming more positive. So in a sense, you get these different charged ions migrating into each of these beakers to even out this change in charge as electrons move. So say I have a electrochemical cell where the cathode is copper. So what I would have then is I'd have copper metal as the cathode and I'd have it in a solution of copper sulfate. So again, at the cathode, there's a reduction reaction. And so over time, we're going to have more positively charged ions coming into the beaker from the salt bridge as electrons come into the cathode. And maybe these ions are something like sodium. And that brings up an important point. You want ions in the salt bridge to be non-reactive. You want them to be inert with respect to the ions that are already in that solution. Now, what do I mean by this? What I mean is that in this beaker, in this cathode compartment, I have sulfate ions kind of floating around, SO4. I have also copper ions floating around. And so when I have sodium ions then enter into that compartment through the salt bridge, that's fine, right? There is no reaction there. The sodium isn't going to form some compound with sulfate, isn't going to form some compound with copper. However, let's say that I'm dumb and I put calcium ions in the salt bridge. What's going to happen then is these calcium ions are going to make their way into that cathode compartment, and calcium sulfate is actually an insoluble material. So what's going to happen then is you're going to start precipitating out calcium sulfate as this reaction progresses, and that's not going to be good for you, right? Because the whole point is that you want to bring in positive charges into that cathode compartment. Well, if you're just bringing in calcium and it's reacting and getting pulled out of solution, that's not helping you. So an important thing to remember is that you want the ions in the salt bridge to be inert with respect to all the different components in the cathode and anode compartments. I want to mention here too that you may see an electrochemical cell represented in something called cell notation. So that is where you will see the name of a metal along with a bar, like a straight up and down line, and then the name of the metal ion, then a double bar, name of the metal ion solution, and the name of the metal. So what this represents is essentially the whole electrochemical cell in this little form. So I've seen it on the MCAT, on some of the practice stuff. I think it's important. So what cell notation is that it is the anode metal, then a straight up and down line or a bar, and then the anode solution, which is going to be a metal ion, then a double bar, and the double bar stands for the salt bridge. And then you have the cathode solution, and then a single bar, and then the cathode metal. So it's going to look something like zinc solid bar, zinc 2+, double bar, copper 2+, single bar, copper solid. And that would indicate that you have an electrochemical cell in which you have a zinc anode, a copper cathode, and it has a salt bridge. All right, so before I get into the thermodynamics of these electrochemical cells, you need to understand a few terms. Those terms are oxidation potential, reduction potential, and cell potential. So reduction potential is the ability of a compound to take electrons. And I've already talked about that quite a bit, but what I haven't said is that this can be given an actual numerical value. So you may be given a chart of standard reduction potentials at 25 degrees Celsius, and it gives reduction potentials in volts. So for instance, fluorine, or F2, has one of the highest reduction potentials, and that is 2.87 volts, whereas lithium has one of the lowest reduction potentials, which is around -3 volts. Oxidation potential, on the other hand, is the ability of a compound to give away its electrons. And this has the opposite trend as a reduction potential. And in fact, if you want to convert a reduction potential to an oxidation potential, all you do is multiply the reduction potential by -1. So for instance, fluorine would have a oxidation potential of -2.87 volts, whereas lithium would have an oxidation potential of around 3 volts. The cell potential, or sometimes represented as E subscript cell, is a measure of the potential difference between two half cells in an electrochemical cell. And I'll talk about how you calculate that in a second, but just understand that this is essentially the potential for the whole cell, including both the anode compartment and the cathode compartment. And this is what would be measured if you were to place a voltage meter in the wire that connects the cathode and the anode. All right, so just to summarize everything from this intro, for galvanic or voltaic cells, the flow of electrons is spontaneous, whereas for an electrolytic cell, the flow of electrons is non-spontaneous, and therefore you need some kind of external source of voltage. A concentration cell is a type of galvanic cell that uses different concentrations of metal ions in the cathode and anode compartments, but it has the same metal cathode and anode, the same electrode. Remember the mnemonic red cat grr king, and then also remember that cats are positive, because who doesn't love cats? And then lastly, remember that salt bridges are required to even out the charge, the net charge, between the anode and cathode compartment.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
All right, so let's get into some thermodynamics now. And I want to start by introducing half reactions and full reactions. So half reactions are either the oxidation or reduction reaction components of an overall reaction. And so a half reaction essentially shows you what's going on at each individual cathode and each individual anode. And this reaction is going to include electrons as either a product or a reactant, depending upon whether it's reduction or oxidation. But a full reaction is not going to include electrons, right? That's just going to be metal ions for these electrochemical cells. So for instance, a half reaction would be the following. Copper 2 plus 2 electrons makes copper solid. And you can think about this for a second. Did I just describe the half reaction for the cathode or for the anode? In this case, we have a reduction reaction occurring, right? Because the copper is gaining 2 electrons. And so we know because of red cat, reduction occurs at the cathode. Therefore, we're talking about the cathode in this instance. So if we have a copper zinc electrochemical cell, then we know at the cathode we have this copper 2 plus 2 electrons makes copper solid. We have that occurring at the cathode. And so we know then that at the anode we have zinc being oxidized. So that half reaction would then be zinc solid goes to zinc 2 plus 2 electrons. Now for the full reaction, we put these two pieces together. The electrons cancel out and you're left with copper 2 plus zinc solid goes to copper solid plus zinc 2 plus. And this full reaction tells you really everything you need to know about this electrochemical cell. It tells you the identity of the cathode, it tells you the identity of the anode, and then it tells you how many moles of electrons are being transferred per mole of reactant, in this case 2. Before I really get into calculating, Gibbs free energy, for instance, of an electrochemical cell, you need to know how to calculate cell potential. And as I said before, cell potential is the difference in potential between the two half cells of an electrochemical cell. And it's measured in volts typically. And so how you calculate this is you say that the potential of the cell, or the cell potential at standard conditions, is equal to the standard reduction potential at the cathode minus the standard reduction potential at the anode. And I should mention that standard conditions for an electrochemical cell is that the concentrations in the cathode and anode compartments are both 1 molar, and the pressure is 1 atmosphere, and the temperature is 25 degrees Celsius. So those are the standard conditions. And it's at these standard conditions that you are typically given a chart of reduction potentials for different components that you can then use in order to calculate cell potential. So for example, take again our copper zinc electrochemical cell. Copper has a reduction potential of 0.34 volts, whereas zinc has a reduction potential of negative 0.76 volts. And now I use my handy equation that says that the potential of the cell, or the cell potential, is equal to the reduction potential of the cathode minus the reduction potential of the anode, to say that the cell potential of the cell is equal to 0.34 volts minus a negative 0.76 volts, and that is equal to 1.1 volts. Easy money. And I should note that in order for a cell to be galvanic and to be spontaneous, you have to have a metal at the cathode that has a greater reduction potential than the metal at the anode. So that's something to keep in mind, because sometimes the MCAT may not specify which metal is the cathode and which is the anode, and you're gonna have to look at the chart and say, okay, this metal has a much higher reduction potential than the other. That's gonna be the cathode. And so going off that, if you have a cell potential that is greater than 0, then you have a spontaneous or galvanic cell. And if you have a cell potential that is less than 0, then you have a cell that is non-spontaneous, and this cell is then considered electrolytic. All right, so overall what you need to remember essentially is just that cell potential is equal to the reduction potential at the cathode minus the reduction potential at the anode. All right, so moving on to real thermodynamics. So for a electrochemical cell, the Gibbs free energy can be calculated by the following equation. The change in Gibbs free energy for an electrochemical cell is equal to negative NFE, where E is equal to the cell potential, F is equal to Faraday's constant, or 96,485 coulombs per mole of electrons, and then N is just the number of moles of electrons transferred in the balanced equation for the reaction occurring in the electrochemical cell. So for this zinc copper system that I've been talking about, that's just 2 moles of electrons. So I would memorize that equation, a pretty simple equation. Remember, it's got a negative sign out front. And keep in mind that for a spontaneous process, that's a process that has a delta G, or a change in Gibbs free energy, that is less than 0, so it's negative. And so it makes sense then that for galvanic or voltaic cells, that the Gibbs free energy is negative. Whereas for electrolytic cells, the delta G is greater than 0 because it's a non-spontaneous process. The next thing that I want to talk about here is the Nernst equation, which deals with electrochemical cells that are not at standard conditions. So up until this point, you may be thinking to yourself, Sam, you mentioned concentration cells, but you literally just told us what it was. I haven't heard anything else about it yet. Well, this part's for you, because the best example, or one of the best examples of a non-standard electrochemical cell is a concentration cell. And you can really apply the Nernst equation to these cells to understand how they work. So the Nernst equation says that the cell potential at non-standard conditions is equal to the cell potential at standard conditions minus RT divided by NF times natural log of Q, where R is a gas constant, T is the temperature in Kelvin, N again is the moles of electrons for that electrochemical cell, F, again, Faraday's constant, and then Q is the reaction quotient, which is products over reactants, all raised to the power of their coefficients. And so this equation says a few different things. First of all, it says that if I raise the temperature of an electrochemical cell, I am decreasing the cell potential, right? Because this number that is RT over NF times the natural log of Q is going to be greater when I raise the temperature, and therefore I'm subtracting more from the standard cell potential, meaning that I have a lesser cell potential at these non-standard conditions. So that temperature-wise, that's what it says. More importantly, this equation says that when we change the concentration of products or reactants, we change the cell potential. So again, Q is just equal to products over reactants raised to the power of their coefficients. So let's talk about this in terms of concentration cells. So as I said before, a concentration cell is a cell in which the electrodes are the same metal. You're changing the concentrations that these electrodes sit in at the cathode and the anode, respectively. So if I have electrodes that are the exact same metal, then what is the standard cell potential? Just going to be 0, right? Because again, the equation to calculate cell potential is that cell potential is equal to the reduction potential at the cathode minus the reduction potential at the anode. And of course, if you have the same metal, it's going to be the same, and 1 minus 1 is always 0. So for example, say that I have a concentration cell with copper metal at both the anode and the cathode, and it is in a solution of copper sulfate. And in one compartment, or one beaker, I'm going to have a high concentration of copper sulfate, and then in the other compartment, or other beaker, I'm going to have a low concentration of copper sulfate. And this is actually going to spontaneously drive electrons from the anode to the cathode. And we can use the Nernst equation to tell us which of these compartments will have the higher concentration of copper sulfate. All right, so going back to the Nernst equation then, we have E cell at non-standard conditions is equal to E cell at standard conditions minus RT over NF times ln of Q. So let's just get rid of RT over NF just because that doesn't matter for what I'm about to talk about, and say that E cell non-standard is equal to the E cell at standard conditions minus ln Q. And so if we want this cell to be a galvanic cell, we want the E cell at non-standard conditions to be greater than 0, right? That means it would be spontaneous. That means it would be a galvanic cell. So that means that we want E cell standard, which is 0, minus ln of Q to be greater than 0. So if I just say, okay, I know that the standard cell potential for this concentration cell is 0, then I have negative ln Q. So now I know that I want negative ln Q to be greater than 0. And so what numbers of Q give me an ln of Q that's greater than 0? Well, that's going to be when Q is less than 1 but greater than 0. So anytime Q is a decimal, I'm going to have an E cell at non-standard conditions that is greater than 0. All right, so now we go back to the definition of Q and we say, okay, we want Q to be a decimal. When is it a decimal? Well, it's a decimal when the denominator is greater than the numerator, or the bottom is greater than the top because it's a fraction. And that means that we want more reactants than products. Okay, great. So we've came to the point where we understand that we need more reactants than products. But now we got to understand what this Q simplifies down to. So if you remember from a chemistry podcast I did, I think probably the thermodynamics podcast, these expressions simplify. So for instance, pure solids do not show up in these expressions. So this expression is going to simplify down, the expression of Q is going to simplify down to the concentration of copper 2 plus over the concentration of copper 2 plus. And so great, now we know we need more copper 2 plus. That doesn't tell us a whole lot. But what it does tell us is that we need to look where the reactant is copper 2 plus, and we need to add more of that reactant in. So in which case oxidation or reduction is copper 2 plus a reactant? Well, it's going to be the reaction copper 2 plus 2 electrons makes copper solid. And that is going to be reduction because it's gain of electrons, and that happens at the cathode. So boom, there you go. We have solved the concentration cell. A concentration cell, in order to run spontaneously, needs a higher concentration of copper 2 plus ions in the cathode compartment than in the anode compartment. And so that goes for any concentration cell, not just this copper 2 plus example. Any concentration cell needs a greater concentration of metal ions in the cathode compartment than the anode compartment in order to run spontaneously. And so that's how you can use the Nernst equation to get to the point where you understand which component of the electrochemical cell needs a higher concentration. You can also reason it out another way. And this is a more of a conceptual way to understand it. But essentially what's going on in a concentration cell is that electrons are transferred from the anode to the cathode in order to balance out the concentrations of ions in both of these compartments, right? The cell wants to reach equilibrium. In order to do that, it wants to even out the concentration of ions in the anode and cathode compartments. And so what are you doing by moving these electrons? Well, you're moving electrons in order to then react with copper 2 plus ions to then form copper solid. So what is that doing to the ion concentration in the cell? Well, it's just lowering it, right? Because you're taking copper 2 plus ions out of solution and making solid copper. So that's over time going to lower the copper 2 plus concentration. And so that should make you think, okay, I'm transferring electrons now from the anode to the cathode, and I'm having a reduction reaction occur at the cathode. And what is the reduction reaction going to do? It's going to decrease the amount of copper 2 plus in solution. And so then that should make you think, okay, well, that's going to have to be the one that starts at a higher concentration because I'm lowering that concentration. Meanwhile, in the anode compartment, I'm actually raising the concentration because I am converting the solid copper to copper 2 plus ions. So you can memorize that maybe and say, okay, I know in a concentration cell, the cathode compartment needs to have the higher concentration, or you could just reason it out. I think the point of the MCAT is not to just memorize these different things, it's to be able to apply them. But, you might have to do a little more work to understand this conceptually if it's not making sense now. There's a great YouTube video that I watched that helped me understand this. You can go on YouTube and you can type concentration cells and cell potential calculations. And the video is by the Organic Chemistry tutor. So overall, a concentration cell is a spontaneous cell with the same electrodes, but these electrodes are in different concentrations of metal ions. And electrons flow from the low concentration side to the high concentration side. In other words, the anode compartment has a low concentration of ions, whereas the cathode compartment has a higher concentration of metal ions. I would understand the Nernst equation, how it describes cell potential at non-standard conditions. And I would understand how to use the Gibbs free energy equation to then calculate Gibbs free energy changes for these different electrochemical cells depending upon what their cell potential is. And as always with these Gen Chem topics, if you're struggling, do a bunch of practice problems. You can hear me talk concept all you want, and you could listen to this podcast over and over. But in the end, what's really going to help you, and I think what is important for the MCAT, is really being able to solve problems. So if you're struggling, definitely go do some practice problems. The next thing I want to talk about here are a few applications of electrochemistry you may see. I haven't talked about electroplating yet, and there's a few equations that go along with electroplating that are important, so I'll discuss that. And then I will talk about a few applications in medicine. It's a pretty short little bit, but hopefully somewhat interesting. So electroplating is a process that uses an electric current or an external source of voltage to reduce dissolved metal ions so that they form a thin metal coating on an electrode. So when you hear the term external voltage or electric current that you're supplying, that's going to be an electrolytic cell. And this is an electrolytic process that requires energy, i.e. it is non-spontaneous. So for example, if you wanted to take an electrode that was, let's say, calcium and coat it in gold, you could do that, right? And that's actually how most people do grills or make their own grills, right? They just stick their face in, a gold ion solution, run a little electricity through them, and boom, you're coated your teeth in gold and it looks great. And so the equation that you need to know for electroplating is one that's called Faraday's law of electrolysis. And this law says that N is equal to Q divided by Z times F, where N is the moles of product, which is the moles of metal that is deposited on the cathode, and then Q is the current times time, and then Z is the moles of electrons that are transferred in the balanced chemical equation as always, and F is Faraday's constant, 96,485 coulombs per mole electrons. And so if I expand this equation and just plug in I times T, or current times time, for Q, I get N is equal to current times time divided by Z times F, moles of electrons times Faraday's constant. And so given a current and given an amount of time that you're electroplating something, you can tell how many moles of product, and of course from that you can determine grams or mass of product is deposited on that electrode. So that's pretty interesting. Maybe you could even be given the number of moles deposited, and you had to determine the amount of time that took to be deposited. And I don't think this is a super important equation to memorize. I think you'd probably be given it. It is simple though, so you could always memorize it. But there's also another way you can get to the same point and you can get the same answers just by using units. And if you want to see this method, you can go to YouTube, type in electrolysis and electroplating practice problems. And it's by the same person I talked about earlier, the organic chemistry tutor. I could describe kind of this method, but I think it's better to just see it. And, I always use this equation, but I think it brings up another good point, which is if for whatever reason you can't quite remember the right equation, look at units, right? You know that units have to cancel out, and eventually you have to get the units of whatever answer that you're looking for. So, if you're looking for seconds, you know that the units of your answer must be seconds. And so that can kind of help you figure out an equation if for whatever reason you can't quite remember the right equation. All right, so again, Faraday's law says that the moles of metal deposited on a cathode through electroplating is equal to the current supplied times the time of the electroplating process, all divided by Z, which is the moles of electrons transferred, times Faraday's constant. In terms of electrochemical cells in medicine, they're mostly used for measuring different electrical processes in the body. So, for instance, you can stick electrodes in like a neuron, and you can measure its change in potential throughout an action potential, which is pretty interesting that they can design electrodes that are small enough to actually, measure changes at the single cell level. That's pretty impressive. It can also be used to measure exocytosis. So I was reading this paper that said that this type of measurement, quote, relies on the oxidation of molecules released at the electrode surface located close to the cell membrane, end quote. And that was in a paper titled Modern Electrochemistry in Nanobiology and Sensorics by Sholducho et al. And what's interesting is this was first done in the 1990s. So this is not something that's like brand new technology, which is kind of interesting. I would think that this would be like nano-sized electrodes and only recently been done. The other place where this may show up in medicine is the most obvious place, which is in battery-powered devices like pacemakers, because batteries are a kind of type of electrochemical cell. I don't understand them that well, and I don't think it's important for the MCAT to understand the anatomy of a battery, but you can understand obviously that the battery is a type of electrochemical cell, and those power things like pacemakers. All right, that is it for this podcast on electrochemistry. As always, if you like what we do, go leave us a review on iTunes. It helps in the rankings. It helps more students reach us. And I always like seeing, nice reviews or not nice reviews. It doesn't matter, but I always appreciate that feedback. As always, thanks for listening, and I hope you found this podcast helpful.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school,